Section: Contents. In this section, we introduce our work on video generation technology, which has gained significant attention since OpenAI launched Sora. This interest has led to rapid advancements in the field, with models now capable of producing videos comparable to professional content. These developments have improved content creation efficiency and reduced production costs, largely thanks to contributions from the open-source community. Projects like Hunyuan Video, Mochi, and Cog Video X have made their foundational model codes and weights available, helping to close the gap between open-source and commercial models. However, we recognize that a gap still exists in three main areas. 1. Performance. Commercial models often outperform open-source ones due to more extensive development resources. 2. Capabilities. Most foundational models focus on general text-to-video tasks, which limits their effectiveness for diverse video creation needs. 3. Efficiency. Many models, despite their capabilities, are not practical for teams with limited computational resources. To tackle these challenges, we present a new series of high-performance foundational video generation models called WAN. Our design is inspired by the success of diffusion transformers combined with flow matching, which has shown significant performance improvements in both text-to-image and text-to-video tasks. We utilize cross-attention to embed text conditions and optimize the model for computational efficiency and precise text control. Additionally, we incorporate a full spatio-temporal attention mechanism to better capture complex dynamics. Through extensive testing, we validate our model at a scale of 14 billion parameters, training it on a vast dataset of billions of images and videos, totaling trillions of tokens. This training enhances the model's capabilities in various areas, including motion quality, visual text generation, camera control, and stylistic diversity. We also expand WAN's functionality to include tasks like image-to-video generation, instruction-guided video editing, real-time video generation, and audio generation. To improve accessibility, we introduce a smaller 1.3 billion parameter model alongside the larger one, both supporting 480p resolution and enhancing inference efficiency. The smaller model requires only 8.19 GB of VRAM, making it compatible with many consumer-grade GPUs while outperforming larger open-source models. We will share the entire training process, including data construction, training strategies, and evaluation algorithms, to support the community in developing specialized video models. We will also provide detailed design information and experimental results, highlighting key findings from our resource-intensive training. We believe these contributions will significantly advance video generation technology. In the related work section, we discuss the evolution of large-scale video models, particularly those based on diffusion techniques. We categorize the advancements into closed-source models developed by major tech companies and contributions from the open-source community. Closed-source models, like Sora from OpenAI and others from companies like Kuaishou and Luma AI, have set high standards for video generation. We note the competitive landscape, where our open-source WAN model has shown comparable or superior performance against these commercial models. The open-source community has also made significant strides, particularly in diffusion-based video generation, which typically involves an autoencoder, a text encoder, and a neural network optimized through diffusion. We highlight various architectures and techniques that have emerged, including adaptations of UNet for video generation and the use of advanced autoencoders for better performance. In WAN, we have carefully selected and designed each component to ensure high-quality video synthesis. We provide detailed design information and studies that can aid in the development of future video generation models. Additionally, we explore various downstream tasks in video generation, demonstrating excellent performance across multiple applications. Section Summary. In this section, we discuss the rapid advancements in video generation technology, highlighting the emergence of high-performance open-source models like WAN, which address existing gaps in performance, capabilities, and efficiency compared to closed-source counterparts. We also review significant developments in both closed-source and open-source models, emphasizing the competitive landscape and our contributions to enhancing video generation through innovative architectural designs and extensive training methodologies. Section: Data Processing Pipeline. In this section, we describe our data processing pipeline, which is crucial for training large generative models. We recognize that high-quality data is vital, and we have developed an automated pipeline to improve training efficiency. Our dataset focuses on three main principles: high quality, high diversity, and substantial scale, resulting in billions of videos and images. For pre-training data, we gathered and cleaned a candidate dataset from both internal copyrighted sources and publicly available data. Our aim was to select high-quality and diverse data from this large, noisy dataset. We implemented a four-step data cleaning process that emphasizes fundamental dimensions, visual quality, and motion quality. In terms of fundamental dimensions, we filter data based on key attributes of the videos and images. We use a lightweight text detection tool to measure text coverage, filtering out content with too much text. We also employ an aesthetic classifier to quickly assess image quality, removing low-quality data. Our internal safety model evaluates and filters inappropriate content based on NSFW scores. We detect and crop watermarks and logos, remove black borders, and filter out overexposed images. Additionally, we have a classifier to identify and exclude synthetic images, as even a small amount can harm model performance. We also assess blur and enforce constraints on video duration and resolution, ultimately eliminating about 50% of the initial dataset. The remaining high-quality data undergoes further refinement based on visual quality. We select data that meets pre-training standards and aligns with natural data distributions. We cluster the data into 100 smaller groups to process them individually, ensuring we don't lose important segments. Each video or image is assigned a quality score, which helps in selecting data for further processing. For motion quality, we aim to select videos that exhibit natural and significant motion while avoiding static or shaky footage. We classify videos into 6 tiers based on motion quality, from optimal motion to low quality and shaky footage, systematically excluding the latter from training. Additionally, we introduce a new approach for visual text data processing to enhance text generation. We synthesize millions of images with Chinese characters on a white background and collect real-world text containing images. Using multiple OCR models, we accurately extract text from these images and videos, feeding this content into our multimodal language model, Qwen2VL, to generate natural descriptions. By combining synthetic and real data, we improve our model's ability to generate accurate and realistic visual text, showcasing our approach's effectiveness. Section Summary. In this section, we outline our automated data processing pipeline, which emphasizes high quality, diversity, and scale in curating a dataset of billions of videos and images for training generative models. We detail our 4-step data cleaning process, focusing on filtering out unsuitable content based on visual and motion quality, and introduce a novel approach for enhancing visual text generation by combining synthetic and real-world data. Section: Post-training data. In this section, we focus on post-training, aiming to enhance the visual quality and motion dynamics of our generated videos using high-quality data. Our data processing pipeline employs different strategies for static and dynamic data. For image data, we optimize it to improve visual quality, while video data is processed to refine motion quality. For image processing, we start with high-scoring images and refine them to select the best samples based on quality, composition, and detail. We create our curated dataset using 2 methods: expert-based collection, where we choose the top 20% of images based on expert model scores while considering style and category for diversity, and manual collection, where we gather high-quality images from various sources to fill gaps in our dataset. This process results in millions of curated images. In video processing, we use a similar approach to collect top-quality videos. We filter out high-ranked videos using a visual quality classifier and then select millions of videos with both simple and complex movements based on a motion quality classifier. We ensure category balance and diversity by selecting data from 12 major categories, such as technology, animals, and vehicles. We also recognize that while our dataset includes text descriptions from original web pages, they often lack detail. To address this, we develop an internal caption model to generate more descriptive captions for each image and video. We train this model using both open-source vision language datasets and additional in-house data. For our open-source dataset, we gather widely used vision language datasets, including caption and visual Q&A datasets. We also collect pure text instruction data to improve our model's ability to follow specific user instructions. Our in-house dataset focuses on enhancing the model's capabilities in recognizing celebrities, landmarks, and movie characters. We compile thousands of identities using large language models to collect names and retrieve corresponding images. We test various models and find that team performs well in recognizing individuals, especially Chinese celebrities. We also implement keyword matching to reduce noise in our dataset. To improve visual counting, we create a counting dataset by retrieving images with text descriptions that include numerical words. We extract category and count pairs from the text and use grounding deno to count objects, retaining images that match the results. For OCR, we enhance our model's text generation capabilities by collecting an OCR augmented image caption dataset. We use an OCR detector to extract text from images and prompt our caption model to generate descriptions based on this text, currently focusing on English and Chinese. We also address the challenges MLLMs face in predicting camera angles and motion by annotating a set of videos for these aspects. This dataset can be used to train our caption model or an expert model to annotate more video data, improving our model's accuracy in motion and angle descriptions. To enhance recognition of fine-grained categories like animals and vehicles, we create a dataset with millions of images. We also gather data focusing on spatial relationships to improve our model's relational understanding. We curate a recaption dataset to extend brief tags into detailed descriptions, and we collect datasets that describe differences between images and provide group descriptions for sets of images. Finally, we gather human-annotated dense captions for both images and videos, which represent our highest quality caption data for the final stage of model training. Section Summary. In this section, we outline our post-training data strategies aimed at enhancing video quality and motion dynamics through high-quality curated datasets. We employ distinct methods for image and video processing, including expert and manual collection of images, and a balanced selection of videos based on motion quality, while also developing an internal caption model to generate detailed descriptions for our dataset. Section: Model Design. In this section, we describe our model design and architecture. Our caption model follows a LLAVA-style framework, utilizing a vision transformer, VIT encoder to extract visual features from images and videos. These features are processed through a two-layer perceptron before being input into the Quen language model. For images, we use a dynamic high resolution, dividing each image into up to 7 patches. We then adaptively pool the visual features into a 12 by 12 grid to minimize computation. For videos, we sample 3 frames per second, with a maximum of 129 frames. To further optimize computation, we implement a slow-fast encoding strategy, keeping the original resolution for every 4th frame and applying global average pooling to the others. Our experiments on long video benchmarks show that this approach improves understanding with fewer visual tokens, enhancing performance from 67.6% to 69.1% on video MME without subtitles. For training, we follow a 3-stage process. Initially, we freeze the VIT and language model, training only the multi-layer perceptron to align visual features with the language model input, using a learning rate of 0.001. In the second stage, we allow all parameters to be trainable. Finally, we conduct end-to-end training on a small set of high-quality data, setting learning rates to 0.00001 for the language model and multi-layer perceptron, and 0.000001 for the VIT. Automatic evaluation is essential for our caption model's development, helping us identify strengths and weaknesses in each version. We create an automatic caption evaluation pipeline based on capability, focusing on 10 key visual aspects in video generation: action, camera angle, camera motion, object category, object color, object counting, optical character recognition, OCR, scene, style, and event. We randomly sample 1,000 videos and their captions generated by our model, also using Google Gemini 1.5 Pro for dense video captions. We evaluate both sets of captions by calculating F1 metrics for each aspect. Our model performs better in video event, camera angle, camera motion, style, and object color, while Gemini excels in action, OCR, scene, object category, and object counting. We also address the challenges of designing effective variational autoencoders, VAEs, for video generation. Videos have both spatial and temporal dimensions, requiring the VAE to capture complex dependencies. The high-dimensional nature of videos increases memory and computational costs, making it hard to scale VAEs for long sequences. Additionally, ensuring that future frames do not influence past frames is crucial for realistic video generation, adding complexity to the architecture. To tackle these issues, we propose a novel 3D causal VAE architecture, called WAN VAE, specifically for video generation. We implement various strategies to enhance spatiotemporal compression, reduce memory usage, and maintain temporal causality, making WAN VAE more efficient and scalable for integration with diffusion-based generative models. To achieve a bidirectional mapping between high-dimensional pixel space and low-dimensional latent space, we designed the WAN VAE to compress the spatiotemporal dimensions of an input video while increasing the number of channels. The first frame is spatially compressed to better manage image data. We replace all group norm layers with RMS norm layers to preserve temporal causality, which allows us to use a feature cache mechanism, significantly improving inference efficiency. Additionally, we reduce the input feature channels in the spatial upsampling layer, cutting memory consumption during inference by a third. By fine-tuning the number of base channels, WAN VAE achieves a compact model size of only 127 million parameters, optimizing encoding time and memory usage, which benefits the training of subsequent diffusion transformer models. Section Summary. In this section, we describe our caption model, which utilizes LLAVA-style architecture with a VIT encoder for visual embeddings, and a slow-fast encoding strategy for video processing that enhances performance while reducing computation. We also introduce our 3D causal VAE, WAN VAE, designed to efficiently handle spatiotemporal video data, ensuring temporal causality and reducing memory usage, making it suitable for integration with diffusion-based generative models. Section: Training. In this section, we outline our training process for WAN VAE, which consists of 3 stages. First, we create a 2D image variational autoencoder, VAE, and train it using image data. Next, we expand this trained 2D VAE into a 3D causal WAN VAE, which gives us a helpful starting point for spatial compression and speeds up training compared to starting a video VAE from scratch. During this phase, we focus on low-resolution videos with a size of 128 by 128 pixels and a small number of features, specifically 5, to enhance convergence speed. Our training losses include a reconstruction loss, a Kullback-Leibler divergence loss, and a perceptual loss, each weighted differently. Finally, we fine-tune the model using high-quality videos of various resolutions and feature counts, incorporating a generative adversarial network, GAN, loss from a 3D discriminator. For efficient inference, we implement a feature cache mechanism in the causal convolution module of WAN VAE to handle long videos. We divide the video into chunks that align with the number of latent features, using a strategy that processes each chunk individually. We limit the number of features in each chunk to 4 to avoid memory overflow. To maintain continuity between chunks, we keep feature caches from previous chunks and integrate them into the computations of the current chunk. We illustrate this process with two scenarios. In the first, we maintain two cached features from previous chunks, using zero padding for the initial chunk. In the second scenario, which involves downsampling, we manage the cache differently to ensure consistency in dimensions while preserving causal relationships. For evaluation, we conduct a thorough assessment of various state-of-the-art video VAE models, measuring their peak signal-to-noise ratio, PSNR, and processing efficiency. We ensure a fair comparison by using the same compression rate and latent feature dimensions as our model. Our results show that WAN VAE performs competitively, offering both high video quality and processing efficiency. Notably, our VAE is 2.5 times faster than the leading existing method under the same conditions, which we expect to improve further at higher resolutions. To validate our video reconstruction performance, we present visual results across different scenarios. WAN VAE excels in capturing details in texture scenes, preserving facial features in facial scenes, restoring text clarity in text scenes, and maintaining motion sharpness in high motion scenes. These results highlight the advantages of our method in handling complex scenarios effectively. Section Summary. In this section, we outline our three-stage training approach for WAN VAE, which begins with a 2D image VAE, transitions to a 3D causal WAN VAE for improved training speed, and concludes with fine-tuning on high-quality videos using GAN loss. We also describe our feature cache mechanism that optimizes memory usage and maintains feature coherence for efficient processing of long videos, demonstrating WAN VAE's competitive performance in both quantitative metrics and qualitative video reconstruction across various scenarios. Section: Model Training. In this section, we provide a detailed overview of the architecture design for our foundational video model, specifically aimed at the text-to-video task, along with the pre-training and post-training phases. We present the architecture of WAN, which is based on the popular DIT architecture, consisting of three main components: WAN VAE, a diffusion transformer, and a text encoder. For a given video, the encoder of WAN VAE transforms it from pixel space into a latent space, which is then processed by the diffusion transformer. The diffusion transformer includes three parts: a patchifying module, transformer blocks, and an unpatchifying module. Within each block, we focus on modeling the relationships between space and time while embedding text information along with time steps. The patchifying module uses a 3D convolution to convert the latent representation into a sequence of features. We utilize a cross-attention mechanism to incorporate the input text, ensuring the model can follow instructions even with long contexts. Additionally, we use a multi-layer perceptron, MLP, to process time embeddings and predict 6 modulation parameters, sharing this MLP across all transformer blocks to reduce the number of parameters by about 25% while improving performance. For the text encoder, we use UMT5, which we found to have several advantages. It effectively handles multiple languages, outperforms other models in composition under the same conditions, and converges faster at the same parameter scale. Based on these benefits, we selected UMT5 as our text embedder. In the pre-training phase, we utilize a flow matching framework to model a unified denoising diffusion process for both images and videos. We start with low-resolution images and then optimize images and videos together in stages, progressively increasing data resolution and temporal duration. The training objective is based on flow matching, which allows us to learn generative processes in diffusion models without needing iterative velocity predictions. During training, we sample a random noise and a time step to obtain an intermediate latent representation. The model is trained to predict the velocity, with the loss function based on the mean squared error between the predicted and actual velocities. Our experiments revealed two main challenges in direct joint training with high-resolution images and long video sequences. Long sequence lengths reduce training throughput, and high GPU memory usage leads to suboptimal batch sizes, causing instability. To address these, we begin training the 14B model with low-resolution text-to-image pre-training to ensure semantic alignment before introducing high-resolution video data. After the initial pre-training, we conduct staged joint training with images and videos, progressively increasing resolution. The training protocol consists of 3 stages. First, we train with low-resolution images and short video clips. Second, we upgrade both to medium resolution while keeping the video duration fixed. And finally, we increase the resolution to high for both images and videos. For pre-training configurations, we use efficient training with mixed precision and the Atom W optimizer, setting the initial learning rate and adjusting it based on performance metrics. Section Summary. In this section, we detail the architecture of our foundational video model for the text-to-video task, which includes components like WAN VAE, a diffusion transformer, and a text encoder. We describe our pre-training and post-training phases, emphasizing a flow-matching framework for stable training and a progressive curriculum that enhances model performance through low-resolution image pre-training followed by joint training with progressively higher resolution video data. Section: Post-training. In this section, we describe the post-training phase where we keep the same model structure and optimizer settings as in the pre-training phase, starting with the pre-trained model. We perform joint training at resolutions of 480 pixels and 720 pixels using the post-training video dataset mentioned earlier. We analyze the workload and find that the computational costs for the text encoder and VAE encoder are lower than those for the DIT model, which makes up over 85% of the total computation during training. The main cost for the DIT model is determined by a formula that includes the number of DIT layers, the micro batch size, the sequence length, and the hidden dimension size. The costs associated with linear layers and attention layers are represented by different factors, with attention costs increasing significantly as the sequence length grows. For instance, when the sequence length reaches 1 million, attention can take up to 95% of the total training time. During training, we only optimize the DIT model while keeping the text encoder and VAE encoder unchanged, which means GPU memory is primarily used for the DIT. The GPU memory usage for the DIT can be described in terms of the number of DIT layers and a factor that varies based on the implementation. This factor is generally higher for the DIT model compared to standard models. For example, while typical models might have a factor of 34, the DIT model can exceed 60. Consequently, with a sequence length of 1 million tokens and a micro batch size of 1, the GPU memory needed for a 14 billion parameter DIT model can surpass 8 terabytes. In summary, the main computational burden in our model arises from the attention mechanism, which increases quadratically with the sequence length, while GPU memory usage increases linearly. Next, we discuss our parallelism strategy. The WAN model consists of 3 parts: VAE, text encoder, and DIT. After optimizing the cache mechanism, the VAE uses minimal GPU memory and can easily implement data parallelism, DP. However, the text encoder requires over 20 gigabytes of GPU memory, so we use model weight sharding to save memory for the DIT module. We combine data parallelism with fully sharded data parallel, FSDP, to manage the model parameters, gradients, and optimizer states, as the DIT's requirements exceed a single GPU's capacity. Given the DIT model's size, we chose FSDP for parameter sharding while optimizing for overlapping computation and communication. The input shape for a DIT block includes dimensions for data parallelism, sequence length, and hidden dimension. We explore sharding strategies for the sequence length and hidden dimension. We achieve sharding along the sequence length using context parallelism, CP, and along the hidden dimension using tensor parallelism combined with sequence parallelism. Since CP has lower communication overhead, we propose a 2-dimensional CP that merges features from Ulysses and ring attention to enhance efficiency. In scenarios with a sequence length of 256,016 GPUs across 2 machines, the communication overhead with our 2D context parallelism drops significantly. The FSDP and CP groups intersect, allowing us to scale effectively. For instance, with 128 GPUs, we set specific sizes for CP, FSDP, and DP to optimize performance. Finally, we address the need to switch distributed strategies for different modules during training. We apply DP to the VAE and text encoder while using a combination of DP and CP for the DIT module. To prevent resource waste, we ensure that devices in the CP group read different data initially, then synchronize the inputs before CP. This approach reduces the time spent on the VAE and text encoder during each model iteration, improving overall efficiency. Section Summary. In this section, we describe the post-training process where we maintain the same model architecture and optimizer as in pre-training, focusing on the DIT model's computational costs, which are primarily driven by the attention mechanism. We also outline our parallelism strategy, employing data parallelism and fully sharded data parallelism to optimize GPU memory usage and computational efficiency across the VAE, text encoder, and DIT modules. Section: Memory Optimization. In this section, we discuss memory optimization strategies. We note that the computational cost increases quadratically with the sequence length, while GPU memory usage increases linearly. This discrepancy means that for long sequences, computation time can surpass the time needed to transfer data off the GPU. Specifically, transferring data from one DIT layer can overlap with the computation of just 1 to 3 layers. To address this, we prioritize activation offloading, which allows us to reduce GPU memory usage without compromising performance. Additionally, since CPU memory can also be strained in long sequences, we combine offloading with gradient checkpointing, focusing on layers that have a high memory to computation ratio. Next, we ensure cluster reliability by utilizing Alibaba Cloud's intelligent scheduling and self-healing features. This allows us to detect slow machines and isolate faulty nodes during training, ensuring that only healthy nodes are used. If any issues arise, tasks are automatically restarted, maintaining system stability and performance. For inference optimization, our main goal is to reduce the latency of video generation. Unlike training, inference involves multiple sampling steps, typically around 50. We use techniques like quantization and distributed computing to speed up each step. We also take advantage of similarities in attention and classifier-free guidance to lower the overall computational load. In our parallel strategy, we implement context parallel to decrease the time needed to generate a video across multiple GPUs. For larger models like WAN 14B, we use model sharding to manage GPU memory limitations. We choose the fully sharded data parallel method for model sharding, as it allows for less communication overhead and computation overlap. We also apply the same 2D context parallelism used in training, achieving nearly linear speedup for the WAN 14B model. We analyze the WAN model's inference process and identify key characteristics, such as attention similarity and classifier-free guidance similarity. We use these insights to implement diffusion caching, which helps reduce computational demands. Specifically, we cache attention outputs and reuse results from previous steps, applying residual compensation methods to maintain detail. This approach has improved our inference performance by 1.62 times. Regarding quantization, we find that using FP8 precision for GEM operations, along with specific quantization strategies for weights and activations, results in minimal performance loss. We apply FP8 quantization across all GEM operations in the DIT block, achieving significant speed improvements. While Flash Attention 3 performs well, its FP8 implementation can degrade video quality. We explore mixed precision strategies to enhance performance and compatibility with Hopper GPUs, planning future optimizations. To address numerical errors in attention with FA3 FP8 quantization, we implement a mixed 8-bit optimization strategy and use float32 accumulation for cross-block reductions. This approach helps maintain performance while improving precision. We also adjust block sizes to manage register pressure, resulting in our 8-bit flash attention achieving 95% memory efficiency on NVIDIA H20 GPUs, boosting inference efficiency by over 1.27 times. Section Summary. In this section, We optimize memory usage during long sequence processing by prioritizing activation offloading and combining it with gradient checkpointing, while ensuring cluster reliability through intelligent scheduling and self-healing capabilities. Additionally, we enhance inference performance by employing techniques like quantization, diffusion caching, and mixed precision strategies, achieving significant speedups in video generation with minimal quality loss. Section: Prompt Alignment. In this section, we discuss prompt alignment, which aims to enhance the effectiveness of our model's inference by matching user input prompts with the style and format of captions used during training. We implement two main strategies. First, we enrich each video with various captions to increase diversity. Second, we adjust user prompts to better fit the distribution of training captions. To support diverse user inputs, we pair each image or video with multiple captions that vary in style and length. For instance, we include long, medium, and short captions, as well as formal, informal, and poetic styles. This variety helps us cover a wide range of potential user prompts. However, we often find a mismatch between the captions in our dataset and the prompts users provide, as users typically prefer shorter, simpler prompts. This difference can negatively impact the quality of the generated videos. To tackle this issue, we use a large language model, LLM, to refine user prompts, aiming to align them with the training captions distribution for better inference performance. The LLM follows specific guidelines. It adds details to prompts without changing their original meanings, enhancing the completeness and visual appeal of the generated scenes. We also ensure that the rewritten prompts include natural motion attributes, adding appropriate actions based on the subject's category for smoother motion in the videos. We suggest structuring the rewritten prompts similarly to the training captions, starting with the video style, followed by a brief content summary, and ending with a detailed description. This approach helps align prompts with high-quality video captions. We evaluate the effectiveness of our LLM-assisted prompt rewriting and present several results. Our findings indicate that LLMs with strong instruction following abilities can create suitable prompts that improve video generation. To balance speed and performance, we choose Qwen 2.5+ as our rewriting model. Next, we conduct ablation studies on key modules in our model to understand their contributions. We perform experiments using the 1.3 billion parameter version for quick evaluation. We focus on adaptive normalization layers, exploring whether to concentrate on parameter volume in these layers or to increase the network's depth. We compare different configurations, including fully shared and non-shared adaptive normalization layers, to see which setup yields better performance. We also examine 3 text encoders capable of handling bilingual inputs: UMT5, Qwen 2.5-7b Instruct, and GLM49b. We find that UMT5 outperforms the others in generating text embeddings, thanks to its bidirectional attention mechanism, which is advantageous for diffusion models. We incorporate a bidirectional token refiner as an adapter layer but still find UMT5 to be the most effective. Lastly, we design a variant of our autoencoder called VAED, where we replace the reconstruction loss with a diffusion loss. We train both the original VAE and VAED on the text-to-image generation task and measure their performance. Our results show that the VAE consistently achieves lower FID scores compared to VAED, indicating better performance. Section Summary. In this section, we describe our prompt alignment strategy, which enhances model inference by rewriting user prompts to match the style and distribution of training captions, thereby improving video generation quality. We also present ablation studies on key model components, revealing that a fully shared adaptive normalization layer design and the UMT5 text encoder yield better performance while reducing parameter count. Section: Image-to-video generation. In this section, we focus on the image-to-video (I2V) generation task, which involves creating a dynamic video sequence from a static image based on a text prompt. This method improves our control over video generation by linking the output to a specific initial feature, attracting considerable interest in the research community. Existing methods like I2V Gen XL, SVD, and COG Video adapt text to video, T2V, frameworks to I2V by combining the conventional latent representation with noise. Our WAN I2V model follows this approach, leveraging the strong prior knowledge from our T2V model to produce high-quality I2V outputs. For our model design, we introduce an additional conditioning image as the first feature to guide video synthesis. We combine this conditioning image with zero-filled features along the time axis, creating guidance features that are compressed into a latent representation. We also use a binary mask to indicate which features to preserve and which to generate. This mask matches the spatial size of the latent representation but has the same temporal length as the target video. We concatenate the noise latent, conditioning latent, and rearranged mask, then pass them through our DIT model. Since our I2V model has more channels than T2V, we add a projection layer initialized to 0. We also use the clip image encoder to extract features from the conditioning image, which are then processed by a multi-layer perceptron to create a global context. This context is integrated into the DIT model through decoupled cross-attention. Our approach can be adapted to other controllable generation tasks, such as video continuation and feature transformation. The masking mechanism clearly defines the input features and specifies which features to generate. To enhance the effectiveness of our masking strategy, we incorporate multiple tasks into our unified framework, including image-to-video generation and video continuation. During the joint training phase, we use the same dataset as for T2V training, which helps the model learn to generate motion based on reference images. In the fine-tuning phase, we create task-specific datasets tailored to each task's needs. For the image-to-video dataset, we discovered that a smaller difference between the first feature and the video content improves model training. We measure this difference using SIG-LIP features, calculating the cosine similarity between the first feature and the average of the other features, retaining only videos that exceed a certain similarity threshold. For the video continuation dataset, we found that training on temporally consistent videos enhances performance. We assess the consistency between the initial and final segments of a video by computing the cosine similarity of their SIG-LIP features and use these scores to filter our training dataset. In the first last feature transformation dataset, we focus on ensuring smooth transitions between the initial and final features, increasing the number of samples with significant transitions in our training data. Section Summary. In this section, we describe our image-to-video I2V generation model, WAN I2V, which synthesizes dynamic video sequences from static images using a masking mechanism to control which features are generated. We also outline our training approach, which includes joint pre-training on multiple tasks and task-specific fine-tuning, ensuring the model effectively learns to generate coherent video content based on the input image. Section: Evaluation. In this section, we outline our evaluation process. We structured the training of the I2V model, including the first-last feature transformation and video continuation, into 2 stages. During the initial pre-training stage, we used the same dataset as in the T2V task. We excluded the image encoder branch to ensure a strong alignment between text and visual output, which helps the model remain sensitive to subtle textual meanings. Once the pre-training stage stabilized, the model demonstrated various capabilities, such as I2V generation and video continuation, indicating that the pre-training effectively built a solid foundation for understanding both spatial and temporal aspects. However, we found that relying only on feature-level information was not enough for optimal performance in tasks like image-to-video generation and video continuation. This limitation showed that while the pre-trained model provided a basic framework for feature-based video generation, it lacked the necessary contextual and semantic depth to maintain temporal consistency in dynamic video sequences, especially when the number of connecting features was limited. To overcome this, we added an image encoder during the SFT stage to extract image features using decoupled cross-attention, which provided global context to enhance the model's capabilities. We conducted experiments using two pre-trained checkpoints at 480p and 720p resolutions, focusing on image-to-video generation, video continuation, and first-last feature transformation tasks. Similar to our human evaluation for the T2V model, we compared our I2V model against state-of-the-art techniques, focusing on visual quality, motion quality, and matching. The results, shown in a table, indicate that our model performed well across all evaluated dimensions. Additional visualizations illustrate our I2V model's superior ability to animate images into high-quality videos. Next, we discuss the Video Connection Unit, VCU, proposed in VACE, which serves as a unified input paradigm for various input conditions, including textual inputs, feature sequences, and mask sequences. We represent this formally, where T is a text prompt, F is a sequence of context video features, and M is a sequence of masks. The features are in RGB space, normalized between -1 and 1, while the masks are binary, indicating where to edit or not. Both F and M are aligned in spatial and temporal dimensions. Using the previously described WAN VAE, we tokenize the input video features and mask information into context tokens. These tokens are combined with noisy video tokens to fine-tune the WAN model. We also propose a context adapter tuning strategy, allowing context tokens to pass through context blocks and reintegrate into the original DIT blocks, enhancing the model's ability to handle diverse editing and generation tasks without changing the base model's weights. Before tokenization, we preprocess pixel-level context features and masks using a concept decoupling strategy, encoding them into the latent space. This strategy separates data from different modalities based on masks into two feature sequences of the same shape, one for reactive features that will be modified and another for inactive features that will be preserved. This ensures clear task definitions and helps the model converge across different tasks. Both sets of features are processed by WAN VAE and mapped into the same latent space, maintaining their spatio-temporal consistency. To prevent mixing images and videos, we encode reference images separately and concatenate them back along the temporal dimension, removing the corresponding parts during decoding. The masks are reshaped and interpolated, and then all features and masks are mapped into latent spaces, aligning them spatio-temporally. In our evaluation results, we demonstrate that the WAN single model performs well across various tasks, achieving high video quality and temporal consistency. We also showcase new applications arising from combining different generative capabilities, highlighting the model's potential for expanding its capabilities. The Unified Controllable Generation and Editing Framework proposed by VACE is applicable to image generation and editing as well. Section Summary. In this section, we describe the two-stage training process of our I2V model, highlighting the importance of pre-training for establishing a strong foundation in image-to-video generation and video continuation. We also address the limitations of relying solely on feature-level information and explain how incorporating an image encoder during the SFT stage enhances the model's contextual understanding, leading to improved performance across various tasks. Section: Text-to-image generation. In this section, we discuss our approach to text-to-image generation and video personalization. We jointly trained our model, WANIS, on both image and video datasets, enhancing its ability to generate videos while also excelling in image synthesis. This dual training allows for knowledge transfer between the two domains, resulting in a highly effective framework. Our model has been trained on an image dataset that is nearly 10 times larger than the video dataset, which has led to significant improvements in image synthesis performance. We have demonstrated that our model can produce high-quality images across various categories, including artistic visuals, realistic portraits, creative designs, and professional product photography. For video personalization, our goal is to create videos that reflect the identity of the user-provided reference. We have integrated advanced personalization techniques into our video generation process, achieving top-tier performance. We will elaborate on our model architecture, the data used for personalization, and the validation of our experiments. Our model design addresses two main challenges: obtaining high-quality personalized identities and integrating these identities into the video generation process. We start with our WAN T2V foundation model and first gather personalized identity information. Unlike existing methods that rely on feature extractors, which can miss important visual details, we avoid using them to prevent information loss. Instead, we directly connect our generation process to the input facial image in the latent space of WAN VAE. We found that using cross-attention is effective for interacting with dense representations from identity extractors, while self-attention works better for data within the same latent space. Our video personalization approach follows a self-attention framework. We extend the video with additional facial images, which we extract and align to a black canvas matching the video size. We then concatenate these images with masks to indicate their presence. The diffusion process is applied to this extended video, guided by the concatenated signals. During training, we randomly drop some facial images to support generating videos with varying numbers of reference faces. In the inference stage, we start with noise and add user-provided facial images, aiming to reconstruct the initial images and create a new personalized video that maintains the provided identity. For our dataset, we curated personalization data from our T2V foundation models training set through careful filtering and automatic synthesis. We filtered out around 100 million videos using human classifiers and performed facial detection. Videos were discarded if they had multiple faces or if a significant portion lacked detected faces. We also calculated similarities between consecutive frames and removed those with low similarity. After segmenting faces and detecting landmarks for alignment, we constructed about 10 million personalized videos, each with an average of 5 segmented faces. To enhance facial diversity, we synthesized additional faces using Instant ID, employing a text template with over 100 prompts. This process allowed us to gather around 1 million videos with synthesized faces, significantly increasing the diversity of styles, poses, and lighting in our dataset. Section Summary. In this section, we describe our dual training approach for the WANIS model, which enhances both image synthesis and video generation by leveraging a significantly larger image dataset. We also detail our video personalization techniques that integrate personalized identity features into the video generation process, ensuring high fidelity and consistency with user-provided references. Section: Evaluation. In this section, we present our results on video personalization, shown in the accompanying figure. The left side displays the input identities, while the right side shows the personalized videos we generated. We randomly selected all testing images from pixels. Additionally, we evaluated our model on a new set of data and measured the similarity between the input features and the output videos by sampling the features at 1 frame per second from the videos. We averaged the final similarity scores from these samples. The results, detailed in the table, indicate that our method performs competitively in video personalization compared to other leading commercial and closed-source Chinese systems. For camera motion controllability, we designed a module that accurately aligns the motion and viewpoint of the video using camera trajectories. We utilize specific parameters for both extrinsic and intrinsic camera settings. Our approach includes 2 main components: a camera pose encoder and a camera pose adapter. In the camera pose encoder, we transform the extrinsic and intrinsic parameters into a sequence of detailed positions for each pixel in the video. To adjust the resolution of the video features, we apply a technique that reduces spatial resolution while increasing the number of channels. We then use convolutional modules to extract multi-level camera motion features. The camera pose adapter integrates these motion features into the video features using an adaptive normalization layer. We convert the camera motion features into scaling and shifting parameters through 2 initialized convolution layers. These parameters are then incorporated into each block of the video features using a simple linear projection formula. For our training data, we employed an advanced camera pose estimation algorithm to extract camera trajectories from videos with significant motion, resulting in around 1,000 video segments. We trained our module within our text-to-video generation framework using the Atom Optimizer. The figure illustrates various examples of videos generated with camera motion guidance. Regarding real-time video generation, we note that current methods often require substantial computational resources and time, making them slow, especially for short clips. High-end hardware systems can take several minutes to generate just a few seconds of video. Although the visual quality has improved, the long processing times hinder practical applications, particularly in fields like interactive entertainment and video production, where quick adjustments are essential. The slow speed also limits use in dynamic environments, such as live streaming or gaming, where immediate feedback is crucial. We aim to enhance real-time generation to improve performance and applicability in fast-paced, interactive settings. To achieve this, we build upon a pre-trained version of our model, which offers two main advantages. It speeds up convergence and enhances training stability, as the model already has a solid foundation. The pre-trained model also retains knowledge about motion patterns and temporal dynamics, which we leverage to improve the smoothness of generated content. To adapt our pre-trained model for real-time streaming, we make two key modifications. First, we replace the static generation process with a streaming mechanism that generates video tokens incrementally. In this setup, as the oldest token is processed and removed, a new token is added, allowing for continuous generation without length limits. Second, we optimize the generation speed to ensure it meets real-time performance requirements, enabling the system to produce new features quickly enough for real-time playback. In the following sections, we will detail these modifications, including their design rationale, technical implementation, and performance results. Section Summary. In this section, we present our video personalization results, demonstrating competitive performance against leading competitors, and describe our camera motion control module, which effectively integrates camera motion features into video generation. We also outline our real-time video generation pipeline, which utilizes a pre-trained model to enable continuous video streaming and optimize generation speed for immediate playback. Section: Streaming video generation. In this section, we discuss our approach to streaming video generation. Traditional diffusion transformer (DIT) models struggle to create videos longer than a few seconds due to the heavy computational and memory demands of attention mechanisms over long time sequences. To tackle this issue, we present Streamer, a new method that uses a sliding temporal window to efficiently handle temporal dependencies, allowing us to generate long or even infinite-length videos in a streaming manner. The main innovation of Streamer is its focus on temporal dependencies within a limited time window. By concentrating attention computations in this window, we significantly lower the computational load while ensuring video continuity. We process video tokens in a queue, denoising them at various noise levels within the window. After a set number of denoising steps, we remove the leftmost token, the one with the least noise, and add a new token with Gaussian noise to the right. This sliding mechanism keeps the window at a consistent length and supports continuous video generation. For training, we fine-tune Streamer from a pre-trained DIT model. We sample a sequence of video tokens, where the first half is used just to warm up the model and does not affect loss calculations. The loss is computed only on the last half, helping the model learn to generate coherent video frames within the window. During inference, we discard the initial tokens and start generating from the next one. To ensure smooth transitions between windows, we reintroduce cached tokens at a noise level of 0. This allows previously generated tokens to help in the denoising of future windows, maintaining temporal consistency in the video. Streamer significantly enhances video generation by adapting DIT models for streaming, enabling the efficient creation of infinite-length videos while preserving quality and coherence. Its advantages include: 1. Infinite-length video generation. The sliding window allows for videos of any length without excessive computational costs. 2. Efficient attention computation. Limiting attention to a specific time window reduces memory and processing needs. 3. Seamless continuity. Caching and reintroducing tokens ensures smooth transitions, maintaining video quality over time. Next, we address the challenge of real-time rendering in our simulated world. While Streamer allows for long video generation, the diffusion process's computational demands can hinder real-time applications. To solve this, we integrate Streamer with consistency models, which accelerate diffusion-based processes. We utilize the latent consistency model, LCM, and its video version, which streamline the original diffusion process into a more efficient four-step model. This integration reduces the number of sampling steps needed for high-quality generation while keeping the temporal coherence and streaming capabilities of Streamer intact. During training, we optimize this combined framework for efficiency and quality, achieving a 10 to 20 times increase in inference speed, allowing for rendering rates of 8 to 16 frames per second. This improvement makes our system suitable for real-time applications like interactive simulations and live video synthesis. Finally, we tackle the challenge of deploying our model on consumer-level devices, which face high computational and memory requirements. We introduce quantization techniques to optimize the model for efficient use. We apply two strategies: int8 quantization for attention layers and linear heads, and tensor-RT quantization for the overall model. The int8 approach reduces memory usage by converting weights and activations to 8-bit integers, but it offers limited speed improvement. In contrast, tensor-RT quantization significantly boosts generation speed, achieving real-time performance of 8 frames per second on a single high-end GPU. However, it may introduce slight errors, leading to minor artifacts or inconsistencies in the generated video. Despite these trade-offs, the combination of int8 and tensor-RT quantization provides a balanced solution for real-time deployment, ensuring efficiency while maintaining acceptable quality. By carefully adjusting the quantization parameters and using TensorRT's error-checking features, we aim to minimize these issues, enabling robust performance on consumer-grade hardware. Section Summary. In this section, we introduce Streamer, a novel approach that utilizes a sliding temporal window to efficiently generate long or infinite-length videos while maintaining temporal coherence, overcoming the limitations of traditional diffusion transformer models. We also discuss the integration of Streamer with consistency models to accelerate the diffusion process for real-time applications, and outline our quantization strategies to optimize the model for deployment on consumer-level devices, balancing efficiency and output quality. Section: Audio Generation. In this section, we focus on audio generation, aiming to create synchronized soundtracks for video clips through a video-to-audio (V2A) generation framework. Our soundtracks include ambient sounds and background music, but we intentionally leave out any speech or vocal elements. Unlike text-to-audio models, the ambient sounds we generate must align with the video's visuals, and the music should match the video's emotional tone and context. To give users more control over sound design, we incorporate both video and text prompts, allowing them to specify sounds and the style of background music. For our model design, we use a diffusion transformer, DIT, to manage the denoising diffusion process in audio. Our V2A model's pipeline is detailed in our figures. We employ an audio autoencoder that converts raw waveforms into MEL spectrograms and encodes them into latent features. However, to fit these features into our diffusion transformer, we must reshape them, which can disrupt synchronization with the video. To overcome this, we train a compression model that works directly with raw waveforms, generating latent features that maintain important temporal information for synchronization. To ensure accurate synchronization between audio and video, we fuse multimodal features. We extract visual embeddings using a clip model and adapt the temporal rate to match the audio features. We then transform these features to align with the latent space of the DIT and combine them. For text understanding, we use a pre-trained model called UMT5, which helps us with cross-lingual representation. Our training data comes from a video generation dataset, where we filter out videos without soundtracks or those containing speech. This results in a refined dataset of about 1,000 hours. We enhance our multimodal representation by using detailed video descriptions and audio-specific captions generated by Qwen 2 Audio, categorizing them into ambient sounds and musical elements. In terms of implementation, our V2A architecture produces high-quality stereo audio lasting up to 12 seconds at a 44.1 kHz sampling rate. We process multimodal inputs through dedicated encoders, generating embeddings of different dimensions. For synchronization, we downsample videos to yield 48 frames for 12-second clips, ensuring accurate alignment between audio and visual elements. We also use a random masking strategy during training to strengthen the model's ability to generate audio from visual cues alone. For evaluation, we qualitatively assess our audio generation against the audio model, which is a competitive baseline. Our V2A model shows superior performance in various aspects, particularly in long-term consistency and clarity of audio output. However, we acknowledge limitations in generating human vocal sounds, as we excluded speech-related data from our training. In future work, we plan to address this by incorporating speech generation capabilities.